let's continue with the non-stationary time series analysis with modern signal processing techniques. And today I want to talk about something slightly different. So recall what is the ultimate goal in time frequency analysis. Technically, we hope that if I give you a signal that is of this format, which is a summation of finite components with amplitude modulation with frequency, instantaneous frequency, then you hope that you can get a plot on the right-hand side that gives you all the information about instantaneous frequency and the phase, amplitude, so that you can recover the signal. That will be ultimate goal. We hope we can achieve it. But how to do it? So if you remember, so far we have talked about several time frequency analysis tools. For example, short-time Fourier transform, which you can find in this YouTube lecture, synchro-squeezing transform, V-shape, concept, or empirical mode decomposition. And actually, there are much more algorithms in time frequency analysis. We will not be able to exhaust everything, but I want to give you a global overview of what's going on without digging into all details. For example, there is a very basic classification of time frequency analysis tools. For example, short-time Fourier transform, continuous wave transform, or S transform, they can be sold as the linear type time frequency analysis. And this linearity has the similar meaning as well what we learned in linear algebra. Or quadratic type time frequency analysis, like Wigner-Ville distribution, ambiguity function, coherent classes, affine classes, and so on. Today we will talk about Wigner-Ville distribution and ambiguity function, and so on. And the linear type includes synchro-squeezing transform, V-shape, and so on, which actually we have covered. We will also want to talk about Brashev decomposition, which use Brashev decomposition or Wigner-Ville decomposition, which is a complex analysis-based approach. But maybe not this May, but maybe August. And there are some kind of polynomial type time frequency analysis, but there will be too much. We will not be able to cover everything. And for most of the types here, we will also not dig into all details, but I will just give you a quick review so that you have a feeling. And when you need it, you know where to find reference and so on. Okay, so Wigner-Ville distribution. So the goal is to get the instantaneous frequency. But so far, as you remember, synchro-squeezing seems to give you something, but not perfect. Okay, so can we have more ideas? Yes, somehow yes. So if you think about short-time Fourier transform and continuous wave transform is something we will cover later, they actually depends on the window or model variant. Okay, that is you choose a window and you truncate the signal into pieces. And over each piece, you do spectral analysis. And then you concatenate all the spectral information you collect from all segments. And you get the final result. That is what you do. But what about if we find a new way to determine a window? That is, the window is actually determined by the signal itself, instead of you have to predetermine a window. Then the idea is Wigner-Ville distribution. What you do is you have the signal, the f, and what you do is, hey, you take function f itself as a window. And you use the window itself to truncate the signal. After the truncation, you evaluate the Fourier transform. That is called Wigner-Ville distribution. That is called Wigner-Ville distribution. Very, very simple. And this is an example of a pure harmonic function. Suppose you have now exponential I 2 pi plus C0t. Very, very nice harmonic function. Okay, and to evaluate Wigner-Ville distribution, by definition, it will just be a Fourier transform of the harmonic function, and what you get will be a distribution, a measure supported at C0. Here, because C0 is 2 pi, so you get just a curve. A 9 at frequency 2 pi. Very simple and nice. And you can consider another example, for example, a chirp. So this is a chirp function, which you have instantaneous frequency 20 plus 4 times t. Okay, so you see the signal oscillates slowly in the beginning and fast in the end. This is a short time Fourier transform. You can see the frequency increases, and and in this example, the Wigner-Ville distribution actually is a very concentrated curve. Which seems quite nice, isn't it? Which seems to be able to help us to get what we desired of the ideal time frequency representation. Looks like a good idea, good solution, isn't it? And there are some very basic properties which you can prove by hand. For example, first, if I give you a real function, then the Wigner-Ville distribution is always real, but it may not be positive. The Wigner-Ville distribution is positive if and only if the function f is a Gaussian function in general. Okay, and you can use it to define instantaneous frequency, which I didn't show here. But the question is it really good? Is it really what everything we want? Turns out, not really, unfortunately. For example, I give you a signal which oscillates at 6 Hertz in the beginning and at pi square Hertz in the second half. And this is the short time Fourier transform where you get two blobs. Not bad, isn't it? But if you take a look at its Wigner-Ville distribution, what do you see? You will see, hey, this is the component associated with 6 Hertz, quite nice. Okay, and this is associated with pi square Hertz, about 9, right? Very nice. But you get a lot of interference. You get interference here. And because it is of real form, so the complex conjugation component will generate a new interference term here, a new interference of these two terms, and a new interference. There will be a lot of interferences appear. A lot of interference. And here is, if you just focus on the complex form of the signal, that is, the signal is exponential I 2 pi 6t plus exponential I pi square t, and you multiply by the Gaussian window. And this is what you get by the Wigner-Ville distribution. You see two components and some interference. And if you pay attention, this interference part actually has a very beautiful interlacing pattern. This is called the Morley pattern, and then this is the signal itself. Okay, and this is the complex form. Yes, this is a complex form. This is a complex form. What is this? Oh, sorry. This is just another representation of this kind. This is the complex form. Okay, and you can see the complex form. You only have two components and the interlacing, and there will be no other interlacings. But here you can see a lot of extra interlacing interferences. So that interference is the main limitation. And if you have two components, the situation may become worse. So here you have two components, cosine, a chirp, and the cosine. But there is no amplitude modulation. And this is a short time Fourier transform. Okay, and this is the Wigner-Ville distribution. You can see two very beautiful curves, very concentrated, but you can see a lot of interference in the middle. This interference limits its application for sure. So can we resolve it? Answer is yes. And we will discuss how to resolve this limitation in a bit, because you can already imagine, oh, the interference seems to have this Morley pattern, so it has some interference. So maybe taking some average, you can cancel it. Yes, that is the main idea. And that is the whole Cohen class basic idea, that you want to cancel all these kind of undesired patterns. And there are some more basic properties about interference. For example, if you have function, you have summation, and just by writing down, expanding, by plugging f into the definition of Wigner-Ville distribution, you can get the Wigner-Ville distribution of each component plus some interference. And this interference, as you can imagine, it is a real part of the interference of first component and second component. Okay, so the cross term sometimes can be viewed as a correlation and so on. Okay, and you can just also try to study the original signals properties using Wigner-Ville distribution. For example, if you integrate over time, then you get the power spectrum. And if you integrate over frequency, then you get the magnitude square of the function in the time domain. So actually it is directly related to time domain and frequency domain, a lot of information. And this is the interference, another visualization. Okay, that you can see if you rotate scenes, then the interference just follow where the two components are. The pattern is actually quite beautiful. It does contain some information. Okay, so what about if you only have one component? Maybe it is because you have two ambitions. You want to study two components so that you see all these challenges. What about if you only have one component? So let's see. If you have only one component, okay, but this time it's 20t plus 8 cosine 2t. In this case, there is no interference in short-time Fourier transform, right? Just one component. Very nice. But unfortunately, in Wigner-Ville distribution, you see it still has Morley pattern. It has a lot of interference. So it is not about one component or two components or multiple components. As long as you have frequency that goes in different directions and so on, it will generate some troubles. It will generate some troubles. And once you have these troubles, it is hard to say what's going on. So we need some modifications. And the spectrogram turns out to be a very, very specific modification of the Wigner-Ville distribution so that we can get something nice from Wigner-Ville distribution. Okay, so if you take a look at the short-time Fourier transform or spectrogram, turns out it's very interesting. The short-time Fourier transform is nothing but the Wigner-Ville distribution convolved with the Wigner-Ville distribution of a Gaussian window. And this is the window edge that is used in short-time Fourier transform. So you see, there will be some oscillatory Morley pattern in the Wigner-Ville distribution. And the Wigner-Ville distribution of the Gaussian window or the window you choose will play the role like low-pass filter, so that the Morley pattern high frequency fluctuation will be cancelled out. So it is a way to smoothing the Wigner-Ville distribution, and that's called spectrogram. So let's take a look how it looks like. Okay, so this is the Wigner-Ville distribution, and that is the Wigner-Ville distribution of the Gaussian window, and that is the convolution. And the convolution is actually nothing but the spectrogram. Okay, there's another view, and this is the code that you can use to generate the result. So this is the Wigner-Ville distribution. Okay, this is 0 Hertz. You have positive frequency and negative frequency, where I show you both positive and negative because the signal is cosine real form, and you can see there a lot of interference. interference. Okay, and this is the Wigner-Ville distribution of the Gaussian window. And this is the result after you run the convolution. Okay, this is the convolution. Okay, and this is the result, and this is the zoom-in. So you can see the relationship is quite beautiful. And as we will discuss later, there are actually several different ways to do this kind of smoothing, and all different smoothings will be combinedly called Coulton class, which we will discuss later. And there are some more basic properties. For example, the support of Wigner-Ville distribution, because we view f, the function itself, as a window, so you can have a differential decomposition. You have a differential theory and write everything in the frequency domain. And from these two patterns, these two equations, you will see that if the support of the signal in time is not a whole line, then the support of the Wigner-Ville distribution in time is the same as that of the signal. And the same fact will hold in the frequency. And this is mathematical formula. That is, the support of f is from -infinity to t0, then Wigner-Ville distribution will be 0 for when time is greater than t0. So you can get some beautiful support properties. This is the property that if you consider short-time Fourier transform, synchronous squeezing, they don't have, because you have to use window. Once you mount a window, then you will always get some leakage to the future. Okay, so this is an example of the support. This is the signal. This is the Wigner-Ville distribution. Okay, and this is more results about Wigner-Ville distribution for linear trend. So this is when signal is 1 is a trend, then you will just get something supported around zero frequency. Okay, and this is the cosine function. You can see the frequency is 2 pi, so you get one component, and around 0 there will be some interference. And if you have a single spike, you have just a spike, then delta 0 short-time Wigner-Ville distribution will also be spike at 0. And this is the kind of also the support property of the Wigner-Ville distribution. So this is when you have 2 spikes, you get 2. Okay, and also interference in the middle. Okay, very good. And the final property will be the reconstruction. Actually, Wigner-Ville distribution has a very nice property that most Coulton class doesn't have. That is, it has the reconstruction property. But it can be it can help you to reconstruct the signal only if the signal f at 0 is non-zero, or when its DC term is non-trivial, then you can recover the signal from Wigner-Ville distribution. So actually, it is kind of nice, but limited. Okay, and also you have energy preservation properties. If you do the double integration and it is Orthogonal, and you have a Moya theory, that is your inner product will be the Wigner-Ville distributions inner product. Okay, and there will be some more properties about quadratic relationship. If you have multiplication, it will give you this kind of convolution type result. And if it is convolution in time domain, it will have the convolution in time domain. So there are several nice properties that you can use, and they looks very much like the relationship in the frequency in Fourier transform. Okay, so let's take a look at its application to real-world data. So if you remember, this is the result we talked in the previous lecture. So this is the PPG signal, and this PPG signal is composed of the motion region and the cardiac component. Okay, so it has 2 components, and both components are actually quite strong. Then let's take a look at what we get. On the top is the synchronous squeezing transform of the signal. You can see several components, isn't it? But in the bottom, you will see, well, I don't know how to do the interpretation, to be honest. It's very, very complicated. It's very complicated. Yeah, a lot of lines, and you don't know which one is which. Yeah, it's difficult for me to do the interpretation. No matter what, you can find it's very basic, very important operator transform. It is widely used in physics and in analysis. So, and you can implement it. You can find time frequency analysis toolbox prepared by Patrick Flangin and his team. And there's a textbook which contains a very detailed exploration of all the topics. And this is another topic called another textbook by Cohen. So in case you need Wigner-Ville distribution or its related results, all this can be helpful. Okay, the final slide is about interference. As I mentioned, Wigner-Ville distribution has this Morley pattern, and we want to cancel it or find a way to cancel it. And can you do it? Yes, you can do it, and you can get some results by just running short-time Fourier transform. Because short-time Fourier transform or spectrogram is nothing but Wigner-Ville distribution combined with the Wigner-Ville distribution of the Gaussian window. That is a low pass. You apply a low-pass filter. Can we apply more? The answer is yes. You can get Wigner-Ville distribution, and you apply some more general kernel function. And for different kernel functions, you will get different algorithms. And overall, this is called Cohen class. And we will come back to this in the next lecture.